Good afternoon, everyone. Welcome to our How Does a Weather Radar Work webinar. For those joining us for the first time, welcome. And for anyone who has joined us for our webinars before, welcome back. Today, we'll be discussing how a weather radar works and what the information is used for. My name is Jordan, and I'll be your moderator today. I'm joined by Claire, whose voice you heard before. She'll be producing today's webinar. Together, we'll help to make the webinar as interactive as possible. So before we start, may I ask for your attention as we cover off some housekeeping items. So with the current situation as it is in Australia, this webinar will be conducted from our respective homes. Please bear this in mind as we may encounter some technical issues during the broadcast. Our broadcast today will run for 60 minutes with plenty of time allocated for questions. And this webinar is also being recorded and the video will be shared with you via email. For first-time webinar attendees, please see some helpful tips on your screen. Most importantly, note the chat box. Now, this is where you can send any questions or feedback for the presenters. Please use this and not the Q&A box to send your questions to us during the session. We want as many questions as you can send us. We will answer as many as possible during the allocated breaks. Now, if you don't know which one it is, it's the little speech bubble button in your taskbar on the screen. The icon will turn blue once it's on, so that's how you know it's working, and then you can send to all panelists so we can see it. If you want to test out how the chat box is working now, feel free to tell us your name and where you're dialing in from. In response to feedback received from some of our previous webinars, here is some information on how to participate in the polls. When a poll is in motion, you'll see a set of questions on the right of the webinar screen. Please select your answer, followed by the submit button below them. I'll also take a moment to thank those of you who sent in questions during your registration process, and we got plenty. We have developed the content of this session in accordance with the common themes that we saw in those questions. So again, thanks for engaging with us. Finally, though, it's time to get to the big show. I'm delighted to introduce you to our presenters, Andrew Collins and Kirsty Turner. Hi, guys.
Hi.
So,
Good afternoon, Jordan and Kirsty.
Kirsty, you can tell we're away, can't you? We're in each other's houses. Kirsty is a trainer of the graduate meteorological course, teaching a number of different subjects, including radar meteorology. She also used radar applications during the forecast process, including forecasting rain for public, marine and aviation industries, and also forecasting and warning for severe thunderstorms and monitoring smoke plumes for emergency services agencies. So plenty of experience. We also have Andrew. He is the manager of the radar engineering section in the Bureau, responsible for the installation, modification and upkeep of the Bureau's radar fleet. Andrew has over 30 years experience in the radar field, managing a wide range of networks and radar types. So you're getting the best of the best today. Hello, guys. Andrew, would you like to start by telling us what we'll be hearing about today?
Yeah, thanks, Jordan. Yes, today I'll be covering our radar network, the radar types in our radar network, and also some of the maintenance that we conduct during the year, and also some of the strange phenomena we see on radar displays from time to time.
Excellent. Really cool. I'm looking forward to hearing all about that. But before we get stuck into the talk, let's test your knowledge about radars with our first poll. So the poll question is, what is the best distance the radar can see rainfall? So is it less than 5 kilometers? Is it 5 to 200 kilometers, 200 to 512 kilometers, or more than 512 kilometers? So please just click which answer you think it is and hit submit. While we do that, we do have some questions, and Matthew has asked the most obvious question. Andrew, I think you're going to take care of this. Why does a radar look like a golf ball? Can you finally answer that burning question for us?
Sure can, Jordan. Yeah, the reason why we have the radome around the radars is mostly for wind protection to the radar itself. The radar is a large dish. It's a solid aluminium dish, and it acts nicely as a sail. So to get the most accuracy out of our radar dish as it's rotating in azimuth and also up and down in elevation, we take the wind load off it, so we put it inside a radome. The radome is round because that's the path that the dish travels in azimuth and elevation. And the dish itself is made out of it's a bit like fiberglass. It's virtually transparent to the radar beams.
All right. Andrew, did you say azimuth then? What does exactly that mean? I know we're speaking to an engineer here, but you've got to help me out.
Our azimuth is rotating around the horizon in 360 degrees.
Okay, easy. So we've also got a question from, and I really hope I'm saying this right, Ing. I'm not sure if I've got that name. I'm really sorry if I've gotten it incorrect. She's asked, any training programs bomb technicians complete to enable them to work with weather radars? Andrew, you also can take that one for us.
Thanks, Jordan. Yes, our radar techs and engineers, we get them off the street as qualified techs or engineers. Once they join the Bureau, they will generally go to our training school in Broadmeadows and do a number of different radar courses. We have about 5 different radar types in the Bureau, and each one of those has a training modules on them. We also have systems at Broadmeadows that we can train the guys on as well. And once they've done that training, they'll then most likely go to a what we call an activity hub in a capital city and Cairns. And from there, that's where they go do the first in maintenance.
Okay, interesting. We still have just enough time for one more question. Kirsty, Fred wants to know, how does the radar penetrate a downpour to get raindrops further into the rainfall area and then still read the reflected signal from those further away raindrops? It's a really deep question. I hope I've said that so it makes sense to everybody. Kirsty, can you answer that, please?
Sure. Okay, so our beam is sent out from our radar, and in the circumstance that it does have to travel through a band of rain or something before reaching the further area of rain, some of the energy actually is lost. That's really dependent upon the intensity, or so the size of the targets, or how many targets there are. So there, unfortunately, there is the issue that some of that energy will be lost going through that first shower of rain, and that's through either scattering of that energy or absorption of that energy. So when we are looking at images where the beam has travelled through a first band of rain, we do need to take that into consideration, that there will be less energy actually reaching that second band of rain.
Okay, interesting. So we do have our poll finished now, and the answer, the question was, what is the best distance the radar can see rainfall? A, less than 5 kilometers. B, 5 to 200 kilometers. C, 200 to 512 kilometers, and more than 512 kilometers. Sorry, was D. Our answers were B, 5 to 200 kilometers. Are we right? That's our most popular answer.
Jordan, they are indeed correct. 5 to 200 kilometres is the
Excellent.
most optimal distance.
Excellent. Well, we're going to really go deep diving into our talk now. Thank you so much for participating in our poll. There is still so many opportunities for you to ask questions as well, so put them in the chat and we will be happy to get them answered. Andrew, you're going to start by telling us about the radars network the Bureau operates.
Thanks, Jordan. Yes, currently the Bureau has 62 WeatherWatch radars in our network. We have the 4th biggest network in the world. That's behind the United States and China, which have around 160 radars in their network. And then the 3rd is Russia. They probably have a handful more than us. But we have 62 in operation. We have a combination of Doppler radars and Doppler radars that are dual polarized, and also conventional radars as well. And I'll cover those a bit more in depth when we go throughout. But generally speaking, a Doppler radar on the Bureau's radar network page will be a black diamond, and a non-Doppler radar will be a red triangle. So as you see on the picture on your screens, that's pretty much our radar network. And the circles you see around those particular radars are their coverage, that coverage is around 3,000 metres above sea level. That is our optimal coverage. You also see that some of the sites are actually you don't have a full circle around the radar. That is due to the location of the radar. The radars, a lot of the radars are located, particularly the older radars, are located at meteorological offices, which are located at airports. A little bit of a history lesson here. Back in 1948, the Bureau bought its first radar from Britain. We installed it at near Essendon Airport. And what we used to use the radars for back in those days, all the way up till not too far off the current day, was tracking balloons. So we used to put a balloon up with a radar target. We would track the balloon till it goes to the upper atmosphere and bursts. From that, we would work out the wind directions and speed in the upper atmosphere. In the last few years, we've automated that process with automatic balloons. So now our radars are now what's known as weather watch radars. So all our radars have ceased wind finding operations. They're now weather watch. So the reason why we don't have the full circle around there is because where the Met Office was located, the Meteorological Office was located at the town's airport, there may be some obstacles in the way now. Things like buildings, trees. Of course, the mountains were always there, but mountains were are part of these obstacles. So a place like Alice Springs, for example, you see in the middle of the display, the McDonnell Ranges is to the north of the airport, so that cuts in on that the lowest elevation on the radar. So that's why you don't always get what you see on here is the optimal coverage is a full circle. We're all the time we're improving the radar network. We're replacing aged radars. We're putting in some new radars from time to time. This is a picture of our newest radar at Rainbow, which is in the Wimmera in Western Victoria. This radar is a new dual polarized digital Doppler radar. I'll explain that a little bit more later. The reason why we put this radar in is because it fills a significant gap between Adelaide, Mount Gambier, Mildura, and Yarrawonga and Melbourne radars. So out in Wimmera, we used to have a bit of a black hole where the radar coverage was. Now we've got the Rainbow radar, covers it in nice, really nice, and we get a contiguous coverage all the way from South Australia all the way over to Melbourne into Gippsland as well. It's a C-band radar. We operate our radars in two different frequency bands. We have C-band and S-band. What that means, C-band is operates in the frequency spectrum of 5600 to 5650 megahertz, and our S-band radars operate in the 2700 to 2900 megahertz. They're a lower frequency radar, S-band radars. They generally have a bit more punching power in monsoonal areas, so they will punch through higher density weather. However, their definition is not quite as good as a C-band radar, but with the modern digital processing, they're pretty much both the same now. It's a 1 degree beam width radar, which means it's got a very large antenna, highly accurate. It puts out a 1 degree beam, so it spins around. It starts at half a degree off the horizon. Then it goes up into 14 elevations throughout its 6-minute scan period. So it builds what they call a volumetric picture, starting at half a degree all the way up to 30 odd degrees of the atmosphere, what's happening in the atmosphere. How do radars work? Yeah, okay, radars generate ultra high frequency microwave radiation. We send out a pulse out of the radar hundreds of times a second, sometimes even thousands of times a second. This pulse goes out the antenna. It's only very short in duration. It's usually around 1 or 2 microseconds, which is 1 or 2 millionths of a second. During the time it's not transmitting, it's listening. So it sends out a pulse, goes out into the atmosphere, and it hits a target. The time that the energy comes back to the radar is the distance how far the target is from the radar. Also, the intensity of the target that it hits will give you either a larger or a smaller signal return. And we work out the direction from where the radar antenna is actually looking. So It can be anything, anywhere from 0 to 360 degrees. So that's where we get our bearing information from. So whereabouts it's coming from. And also we elevate the radar all the way up to about 30 odd degrees. So we get a height information from the radar as well. So that's how radars work. We send out short pulses of energy. We wait for it to listen. We listen for the return echoes, and that's where we get our information from. This slide also shows that the radar picture is three-dimensional. So as you see, it's an animated picture in the middle. It shows you the elevations that the radar goes through. So generally speaking, most radars, elevation starts at 0.5 degree is the base scan. It does a full 360 at 0.5 degree scan, and then it goes up to the next elevation. Bearing in mind, as you go up in elevation, the range of the radar is reduced because you're not following the horizon anymore. You're going up, you're pointing towards space. So the target range is slightly reduced as we go up in elevation. And this is repeated every 6 or 10 minutes, and that's dependent on the radar type. Our newer radars are doing 6-minute scans. So that's why when you see on the internet 6-minute intervals, that's what it's waiting for, is 6 minutes to build up a picture. And some of our older radars take 10 minutes to do that. Those older radars also, they don't do 14 elevations. They may only do 6 elevations. So that's how we build a picture up on what you see on the Bureau website. Okay, for the types of weather radars we have standard weather watch, and they're all, you could all say they have this functionality. And what this means, they do reflectivity. As I said, the ones in the radars with the red diamond, the red triangles, they only do reflectivity. Of course, the radars that are in the black diamond, they also do reflectivity. And what that means, they just pick up what's ever out in the atmosphere that is moving around. So our radars will pick up rain, which includes drizzle and snow and ice. They also pick up smoke, dust, insects, birds. Sometimes you see swaying trees on mountains, particularly when you're looking at the radars along the eastern seaboard. When you're looking along the Great Divide, you might see a clear day and it might be a dewy morning, and you might see a bit of what we call clutter hanging off the mountain range. That'd be trees swaying around that are wet. So we're getting a bit of reflectivity off that. We don't get reflectivity off buildings and mountains because we filter those out because they're not moving. So anything that sort of does anything around 5 kilometres and over is what we let through to process, and that's what you see on the radar display. That's why you don't see mountains and buildings. Sometimes the coastal radars will pick up ships at sea as well because the lower beam will travel out towards the sea. A large ship is moving at X amount of knots, and it will return back a very nice target. It's those familiar with Melbourne, you always see the Tasman ferry going down South Channel as a nice reflective target when it sails. So that's what we call standard weather watch, which is reflectivity only. And of course, the radars that are depicted with the black diamond, they also have Doppler. Now, Doppler, Kirsty will explain a little bit more about Doppler, how it's used in forecasting, but pretty much any target that moves around the radar to and from, towards or away from the radar will be picked up on the Doppler image. And that is useful because it looks at what the upper air is doing, as in what the upper air winds are doing. So any particles in the air, even if it's not raining, we may get some particles in the air and we get returns off those. And what that does, that the return echo will be slightly out of phase to the transmission signal, which means, as you see down the bottom, you see that the pulse and the phase will be slightly move away from the base frequency. If it's slightly higher frequency, it means the target is coming towards the radar. If it's slightly lower, it means it's going away from the radar. And how that's depicted on the website is by blue and yellow, the red tones. So any images, any targets coming towards the radar will be shown as blue. And as they go away from the radar, they'll be shown as red targets. And you'll also notice that in between those two, there'll be a white zone, and that's what we call the zero Doppler. So that's the line where the wind speed travels past the radar where there's no Doppler shift. I hope I wasn't overly too technical with the pulse widths there. Okay, thank you. All right, so the new Doppler radars, we have 8 radars at the moment that are dual polarized. Traditionally, radars, most radars transmit in what they call a horizontal plane. And as you see the picture on the left, you see 2 planes being transmitted, 2 signals. Now, with the dual pole systems, we transmit not only horizontally but vertically. So we send out 2 pulse fronts, 2 wave fronts at right angles to each other. And the use of that is not only we pick up precipitation better, but we also pick up the shape of precipitation better. So rain has a sort of a teardrop shape, hail is round, snow is flatter. So the dual polarized radars can distinguish between those targets better than those.
Now it's over to me. Thank you, Andrew. Okay, so I'm glad I've had Andrew here. He can talk about all the technicalities of radars. And I'm here to talk about how we apply the radar. So I've got here an image of our interface on our webpage that I'm sure all of you have seen before. I know lots of people out in the public do enjoy looking at the radar and having a go at being meteorologists themselves. I wanted just to step you through some of the features on here that you may not have used or been aware of. So let's have a look at some of them now. Now, the image that we've got on the screen there, that's our reflectivity image. So that's our typical rain image. But as Andrew said, that you can also get other reflectivity targets detected. Now, there's a few things to look at here. So this is under the radar image. So if I just move my cursor, hopefully you can all see and follow along. These are the radar choices. So we have 4 different options typically. Not all radars will have all of these options. So we have the 64-kilometre image, the 128-kilometre image, which is what we're looking at right now, the 256, and then the 512-kilometre composite. So the 3 smaller ones, they're all going to be of that particular radar that you have selected. So this one is Melbourne. But if you might notice, if you click on the 512, that's actually a merged image. So what that means is any of the nearby radars we are overlaying together so that we get a bigger radar image, because that 512 kilometres is just too far for one single radar to actually be able to detect reflectivity for us. Now, we also have the national image, so that's a great one to look at. You can actually also overlay the satellite imagery with that one. So that's a kind of nice little tool to use in conjunction. Then we have our Doppler wind at the very end there. Now, as Andrew just mentioned, that's showing us our wind, and I'll go into a little bit more detail shortly. Then on the next line down, we have rainfall. Now, the rainfall you may not have looked at before. The rainfall will actually, these images will be converting the intensity rain rate into estimated total rainfall over a particular duration. So the radar images normally just show a point in time. So for example, this one's at 05 UTC time, universal time coordinate, and that's what's happening right at that moment. whereas the rainfall's actually going to give us accumulation of what's potentially falling at the surface. So you've got the 6 minute, the 1 hour since 9 a.m. and also the 24 hour. Okay, another feature that I'd like to point out is the loops button. Now, all forecasters use looping of radar imagery. It's just a much better way to see how things are developing, how they're moving. It's really a much better way to take in the information than just the static images, although they are still also available. And as you might notice, you can see there's some observations overlaid on our radar image. Now, I always have this toggled on, and so you can do that as well down here under map features. So there's a few different options. Topography is also a good one to have on. You can see where the mountains are, but yeah, certainly weather observations is a good one, and it really to use it in conjunction with the radar imagery is a great tool when, say, a wind change is coming through, or seeing how much rain we've had at a particular location. Okay, so I'll just quickly chat about each one of these. So the reflectivity there, the reflectivity is approximately converted into rainfall intensity. So you can see at the bottom there, we do have a scale going from sort of the whites and light blues through to the yellows and oranges and reds. Now this is indicating the intensity of that rainfall. So that's proportionally to the amount of energy that's being returned to the radar. So it can sort of tell us two things. It's either where the target is a large shape, so large raindrops or potentially hail, or it could actually mean that there's just quite a lot in concentration of these drops. Now, these reflectivity images that you see on our web page is actually a combination of some of the velocity, the volumetric scans. So before Andrew was explaining that our radar samples at 0.5 elevation first, and then it tilts up higher in the atmosphere, and then it keeps going up to around 30 degrees. Now, this image here, we're trying to display the rainfall that's approximately 1 kilometre above the ground. And so to actually achieve this image, we're going to have to join a couple of the lowest scans together to actually represent that 1 kilometre above the ground image. Now, Doppler radar. So Andrew explained that the blue is towards and the yellow, orangey, reds are away. And this is a measure, our Doppler is measuring the change in phase between two particular pulses that have come back to the radar. And that's how it works out whether it's going towards or away from the radar. I do just want to point out that our Doppler radars can only determine the component of the wind that is directed directly towards or away from the radar. So if, for example, the wind is blowing perpendicular, sort of alongside the radar beam, the radar won't actually detect any wind. So I'll try and explain this a little bit more in this image over here on the left-hand side of the screen. So we've got our radar in the center, and this green wind vector is our total wind velocity and direction. So we've got our wind traveling in a southwesterly direction. The radar can only interpret what is this part here, the radial velocity that's coming either in towards the radar or out of the radar. This wind vector here that is perpendicular to that radar beam, we don't have any information about. So this is called our transverse velocity. So just to keep in the back of your mind, if you are starting to have a bit of a play with these images, which I recommend you do, just keep in the back of your mind that the wind speeds, unless that wind is directly going into the radar or out of the radar, it's not going to be that full wind speed. So that's just one little thing to be aware of when you're looking at this data. Now, as far as, and so then also the intensities there on the scale down the bottom of that image, you can see, and it does a little tip there, it does say towards and away with the colors there. Now, just a little tip, like the way I like to remember these colors, because on our displays we don't actually have towards and away written on there, is that I like to think of car lights. So with cars traveling away from you, you see those red tail lights. So to me, I think of the yellow, orange, red colors are away from the radar. So that's just a little tip how I actually help remember these towards and away colors. Now, these Doppler images, we use these to help us track wind changes or even to diagnose severe storm signatures. So they're quite useful, but I certainly do always open it when we've got a good wind change coming through. Now, this was the rainfall accumulation one I was pointing out. Now, this here was actually taken just in the last week when we had some of that decent rainfall over Melbourne. You can see that it's converted into millimetres down the bottom there. So that's the way it's calculated is it combines the radar scans along with actual rain gauge data. So our radar data is very good spatially, but we are estimating how much those reflectivity images are being converted into actual millimetres on the ground. So rain gauges are much more accurate, but the downside is they're a bit more sparse spatially. So we use those two sources in combination to provide a more accurate rainfall estimate. Now, these fields are used by forecasters, hydrologists, emergency services, and these really help us with the distribution and trends of rainfall totals, particularly when we're trying to warn for flash flooding events.
Excellent start, guys. A lot of great information to take on board there. We've got another poll and we're going to jump into a Q&A session now. So we really appreciate all the questions that have been coming in, and we want you to keep sending them in because that's what we've got time for, to really get into your questions, and you don't get many chances to talk to experts. So the poll should be up on the right-hand side right now. It says, what can you detect on a weather radar? We have A, rain, B, smoke, C, wind, D, thunderstorms, and E, all of the above. And as those answers come in, we're going to get to some questions. So Jason, Demetrius, and a whole bunch of other people have asked, what is the difference between a meteorological radar and the ones they use at the airport? Andrew, I think you can handle that one.
Yeah, thanks, Jordan. Yes, I can answer that. The main difference is the internals of the radar is very similar. The radars use the same sort of transmission technology, a magnetron or a klystron. The main difference is in the data processing and also the antenna that the radar uses. With weather radars, we use a pencil beam with a dish antenna. Air traffic control radars generally have a fan beam, so very narrow beam like we do in azimuth, but in elevation, they look at a larger, wider beam because they're looking for a solid metal target over that could be anywhere. So that's why they send out a wider beam in height.
Okay, excellent. Richard has asked, does the radar become less reliable for properties in hilly country or country at a high altitude above 1,200 meters above sea level?
We're going to fight over this one.
You want to take that one, Kirsty?
Yep, sure, no problem. Okay, so does the radar become less reliable? Look, there's always going to be that issue with beam blockage when you start talking about terrain. So it really depends on where that radar is located in relation to the position you're talking about. So sometimes if you are in the lee of a mountain, that we may not actually be able to see sort of the low-lying clouds or precipitation, because that mountain is actually blocking those lower scans. But otherwise, if there's no blockage, then no, there shouldn't be an issue. I guess there's sometimes also sort of almost the opposite issue with if sometimes we have to put a radar, like I think the radar down in Hobart might be quite elevated. And if that's the case, then you're not going to see anything sort of below that radar. So if it's actually positioned on a mountain, then it's quite difficult in those sort of valleys, etc. So other than the beam blocking issue, there shouldn't be any other, it shouldn't be less reliable. It would just be if those images are actually blocked.
Okay. Maurice, I would like to know, and I think this is an Andrew question, are there any radars on Christmas Island?
There is no radars on Christmas Island.
Okay. Simon is interested in knowing, does the same technology that identifies rain also identifies lightning? And if we're going to get into this in the following, don't give us too much information, but can you answer that one, maybe, Kirsty?
So radars detect targets. So because lightning's actually light, we don't actually detect lightning with our radars. It actually has to be a solid target, like a raindrop, even it's something as small as dust or bugs. But no, we can't detect lightning with our radars.
Okay, I think I've just given away one of the poll questions there, but you've still got time to complete that poll. We'll be wrapping that up in a minute while we take more questions. Please keep them coming in. Use the chat function, not the Q&A, so we're able to see it. Okay, so I found this one pretty charming, actually. Jack has sent in that he says, I'm sure like many people, we have our favorite radars that we like to check. He likes to check ones back home in WA to see if there's any snow on the way. Does anybody here, and I'll start with you, Andrew, what's your favourite radar that you'd like to check up on every now and then?
Well, living in Geelong, I obviously like the Laverton radar, but I have like my children, I have no favourites. I love all 62 of them.
And what about you, Kirsty?
I'm also Melbourne-based, so I do regularly look at the Laverton radar, although I do have a bit of a fond spot for the Broadmeadows radar, just because that's where I do some of my training.
Okay, there we go. Jack, make sure you let us know what your favourite is, or if you've got a favourite, we'd like to know. John's a history buff. He wants to know, is the Melbourne radar still located at Essendon?
I can answer that one, Jordan. No, we have two radars in Melbourne. One radar is located at Laverton on the RAF base. So as you're driving along the Princess Freeway to and from Geelong, you'll see it on the over the RAF base. And also the second radar in Melbourne is located at Broadmeadows at the Bureau's training school. And that's our backup operational radar for Melbourne.
Just following up on that, do most capital cities have a backup?
Most capital cities do have a backup. So in the case of Brisbane, for example, the main radar is Mount Staple and the backup radar is Marburg. And however, a couple of the capital cities such as Perth, Darwin and Hobart, the radars that are the backup are located at the airport and they're not always displayed on the internet.
Okay, excellent. All right, well, we've got our poll results now. We had most people say that it's E, all of the above. What can you detect on a weather radar? Now, we do know that thunderstorms isn't one of those. What are the other ones that can be detected on a weather radar, guys?
Jordan, thunderstorms is actually correct.
Oh.
Thunderstorms is different to lightning. I'm being a little bit technical here, sorry.
Okay. Well, you're the expert, not me. You tell it. So it is all of the above.
Yes, I would go with that too, Jordan. However, not all radars can detect wind. So as I spoke about earlier, our conventional Reflectivity radars, the old ones, will certainly pick up rain, smoke, and thunderstorms. Our Doppler radars will pick up the wind.
Okay, well, let's move on from our poll right now onto our next section. And we have started asking a couple of questions, but we have actually allotted this time for questions as well. So there are still plenty here that I thought maybe we can get into. David wants to know the topography around Longreach for about 100 kilometers is perfectly flat and there are no tall buildings. So why does it not have a full circle?
Okay, David, as I discussed earlier, the Longreach radar was installed initially as a wind finding radar. And if you drive past Longreach radar, you'll notice that it's on an 8-metre tower. Now, since it's been installed, some of the trees across the highway have grown in the bush, and we sort of get a little bit of blockage from those on the lower elevations of the radars. As we elevate higher up, we clear those trees, so we do get quite good coverage from Longreach, but that's the reason why you don't get a perfect circle at Longreach on our optimal coverage diagram.
Okay, all right, and one more question before we move on. This one comes from Kieran. He said that the scan geometry is slightly curved. It was that image that we saw moving before. Is that a correction for the Earth's curvature?
Good question. Yes, look, the Earth's curvature does play a part, and I'm going to talk about that really soon. But there is also another part that we need to consider. So when our beam actually enters our atmosphere has different densities, and so therefore it's going to refract the beam. So we need to take this into consideration when calculating the heights of these targets when they return to the radar. So we base this on a standard atmosphere. Now, our atmosphere is very rarely standard. In fact, it's generally not, and so therefore, so the radar is taking into consideration a standard atmosphere, and that is due to the atmosphere actually bending that beam upwards.
Okay, really interesting. All right, we're going to take a pause there for the questions. We'll have another Q&A session coming up towards the end of the webinar. Don't worry, we're going to try and get to as many as possible, even if we have to go a little bit over, because we know how interested you are. And like we said, not often that you get to talk to these two super experts about everything to do with radar. So we will get to your questions as they come through. Kirsty, she's going to race through this section and move into hopefully more questions a little bit later on. You're going to guide us through the limitations of radar.
I certainly will. So there's many great things about our radars, and they are amazing, and we do rely heavily on them as forecasters, but there are some limitations that we do need to be aware of when we are using them. So I've tried to summarize them all on this slide, so bear with me. So look, the first one that we were just talking about is due to the curvature of the Earth. So the elevation of the beam, as it increases with height, the beam increases with distance, so does that elevation. So due to that beam being sent out at an angle and also that curvature of the Earth, the targets far away from the radar are actually quite elevated and therefore could be evaporated by the atmosphere before reaching the ground. Now, this is called virga, and it so we've got this on the image here. We've got this cloud really high up in the atmosphere, and if the atmosphere is dry enough, that those raindrops can actually evaporate, and that's what we call virga. Now, this you won't see very often on the Bureau web page. The targets that you see on there should generally reach the ground, just because we have them based at a fairly low level at 1 kilometre, but the images that we get, sometimes we do need to take that into consideration. Also, as this beam goes out away from the radar, sometimes it can actually overshoot low level clouds. So what that means is the beam is going out above the clouds, and we're actually missing some of that precipitation underneath. So there's that issue as well. The resolution of the beam actually does vary between ranges. So as you can imagine, a beam that goes out is going to spread out in the horizontal and the vertical. So it just means that the detail, I guess, that we're seeing at long ranges might be a little bit more washed out compared to some of the targets that are closer to the radar. Now, the beam, as we've already mentioned, can be blocked due to terrain or mountains, such as mountains or buildings. Now, as Andrew mentioned, we do actually try and remove these targets from the imagery, but sometimes they do, you know, these targets do get through into our imagery. But also we need to be aware, like we mentioned earlier, that you may not see the rainfall in the lee of a range that has been blocked. Now, there's also another issue, as again we've already discussed a little bit about, is attenuation. So as a beam travels through one area of rain, some of that energy is going to be lost. So when that energy does finally reach that second area of rain, so rain area B, for example, there is actually less energy already. And so we are going to have a weaker signal return than perhaps if there was nothing in its way. And also just due to refraction. So we were just talking then about our atmosphere, how it bends that beam, and under certain circumstances, that can actually bend the beam down towards the ground, and that actually produces false echoes, such as something we call ground clutter. Now, this is one, as a meteorologist, I quite often get this comment from friends and family. Why is it raining, but the radar shows nothing? Now, look, the most common reason is likely due to drizzle. Now, those of you that are in Melbourne, yesterday was one of those mornings where you don't see much on the radar, but if you had, headed out for a walk around the block, you would have got quite wet. So when it comes to drizzle, the drizzle is produced by low-level clouds. So first of all, we may not see it because the beam is actually higher than those low-level clouds, but also the droplets, the actual definition of drizzle is that the droplets are less than 0.5 millimetre. So therefore, they're going to send back really weak signals. And so if you look really hard on that radar, you might be able to see a couple of white targets here and there. And if you loop it, you can sort of just see them sometimes. But yeah, that's a very common reason as to why it is raining and there's nothing on the radar. This is the opposite effect. This is where there are rainfall reflectivity on our radar images, and yet there's no rainfall falling at the ground. So a common reason for this is that we're getting these false echoes for whatever reason. It could be buildings or mountains. It could be the ground. The atmosphere has bent the beam down to the ground. It could be due to some dust or smoke or insects or birds or bats in the sky that our radars can't discriminate against, and it'll come up as reflectivity. Now, my tip here would be to always check with the satellite image. If there's no cloud, it's not rain. Now, I thought I'd show you a couple of images on some wind changes. So how do we use the radar? Look, the obvious answer with the radar, how we use it, is to detect where we've got rainfall and maybe where we're going to get rainfall. But there are a number of other reasons or ways that we can use a radar, such as timing of wind changes. So this is an image only taken sort of a handful of days ago when we had a pretty decent wind change coming through Victoria. And this is our northeast Victoria radar up at Yarrawonga. So I've got the observations overlaid on these images here, which I always like to do, and I'd encourage you to do the same. And if you look at the image on the left, the reflectivity, you can see ahead of, or to the east of these precipitation, all of these winds are pretty much northerly winds. So we can tell that from these wind vectors here. And these ones are a little harder to see under the rain, but behind this band of rain, we've actually got southwesterlies or westerlies through here. And this actually ties in really nicely with our Doppler imagery. So remembering that blue is incoming and the orangey reds are the outgoing. So here directly at the radar, we're going to have our incoming winds and then our outgoing winds through this way. So that fits in really nicely with our northerly winds here. And over in this part, we have our westerlies. So we can see we've got these westerlies, so they're coming into the radar. And this is nicely where our wind change is. So we've got our outgoing, so we've got winds coming in this way, and then we've got winds coming in this way. So this is our wind change right here. Now, keeping in mind, it's only the radial component. And if I step forward one, we've moved 40 minutes down the track. So this was at 5:30 UTC. So just a quick conversion, that's like 3:30 in the afternoon. And if we step forward another 40 minutes, so that's about, actually 50 minutes, we're now about 20 past 4 in the afternoon. And you can see, according to the rainfall and the surface observations, that change has moved through Yarrawonga. And if we now, this is where it gets a bit complicated, but we look at our Doppler imagery, we can see we've got our incoming here and our outgoing here. So we're definitely matching up with our westerlies here. And we've still got our incoming over here, over near Corowa. So we've still got our northerlies here. We're meeting up here with this outbound here, and that's where our wind change is. So it's really useful for us when we come to detecting wind changes. Another way we can use our radar is the detection of severe phenomena. So one of them being damaging winds. Now our Doppler imagery here on the right-hand side has got a scale. If you look at the scale down the bottom, it's actually in kilometres per hour. And if we go all the way through to these dark reds, we've reached 90 kilometres per hour. And what happens with our Doppler radars is they have a threshold. There is a wind speed that it can accurately detect. And if you actually exceed that, it's got an issue. Like, how are we going to say that these winds are 100 kilometres per hour, for example? The way that the radar resolves it is by actually jumping back down to the other end of the scale and jumping into these colours. So whenever you're looking at your Doppler data, you've got these yellows, oranges, yellows, they come into this white colour going along the scale here through to the light blues and then into the dark blues, but then it jumps into this red colour. That's because we've actually got winds that are exceeding 90 kilometres per hour and they've jumped back around to the other end of the scale. And so whenever we see a dark blue going to a dark red or vice versa, we actually know that this is aliasing. And for this particular radar, that means that the winds are actually greater than 90 kilometres per hour, and that's damaging winds. So we would have to issue a severe weather warning for that one. Another way we use our radar is to warn for severe storms. So really common, particularly along the east coast of Australia. So we can identify severe thunderstorms by looking at the intensity of the targets, looking at the patterns of the targets, and we can also use this for tracking thunderstorms. So when we issue our warnings, we need to say where the thunderstorm is currently and where it's going to move to. So using those loops really helps us with that trajectory of those storms. And another one that I've been doing a little bit more of lately. I've been working with some of the emergency service departments, agencies in Victoria, and helping with the prediction of fire danger ratings and fire behaviour. So we can also look at the height of these fire plumes. And we can also detect smoke. So this imagery here, if we look at our satellite imagery, we've got this large area of smoke advecting down along the coast here, and you can see it actually also here on our radar. So this isn't rainfall, this is just smoke being detected. I'm going to hand it over to Andrew to explain some of these strange images.
Thanks, Kirsty. That was an excellent overview of how you guys use the radars. Now, from time to time, you'll see some strange images on the web. Nothing sinister about these. It's usually due to a couple of reasons. First of all, we look at the image on the right-hand side of the screen. There's a large strobe to the southeast heading towards Melbourne radar. That is interference, electromagnetic interference from Wi-Fi that's actually operating out of band and into our band of the radar. So the radar picks up that strobe, and we quite often get interference from things that don't comply to the Australian regulations. We also get interference from cruise ships, military operations, and the like. So if you see any strange strobes on the radar, generally speaking, that's electromagnetic interference from an external source. And those with the newer radars filter those out a little bit better than some of the older radars. So that's something to look forward to with the new radars. Now, the images on the middle and the left-hand side of the screen, generally speaking, they're malfunctions of the radar, which means something in the radar, in the case of the middle image with the red dot in the middle, that is a receiver failure. Part of the receiving system has failed, and it's picking up some strange noise generated within the system itself. And generally speaking, as soon as we see that, we turn the radars off the internet and investigate the issue. The image on the left, that's a similar issue. We had a fault on the radar that was injecting a signal into the receiver, and that caused that strange swirl. The bottom image was a issue with a receiver on the radar at near Charleville, where the receiver wasn't working properly. It malfunctioned and it didn't provide any return echoes in its space. We get interference, as I said, from electromagnetic interference from ships, aircraft, military. We're also starting to see a little bit of interference on our Doppler radars from wind farms as well. As we get more wind farms throughout Australia, we get a little bit of interference from those. But however, we're working on filtering those. Okay, maintenance. The radars are very complex machines. There are a lot of high voltage components within them, and they've got huge mechanical antennas that they've got to move around 24 hours a day. So there's a little bit of maintenance that has to be done. Generally speaking, every 6 months, we have two technicians visit the site for a week. They check the system's calibration and make adjustments and make sure the radar's operating as it should, as per its specifications. Whilst they're out there, they do mechanical servicing. So they look at the antenna, the gearboxes and dishes and things like that, make sure it's lubricated, things aren't excessively wearing, and just do general checks like that. So that's done every 6 months. Also, while they're out there, the radar has a number of infrastructure systems as well. So air conditioning, uninterruptible power supplies, and a backup generator. They also make sure they're functioning correctly as well. So there's a lot to do in the week that the two guys are out there in the field. So they're pretty busy. And also, when the radar breaks as well, which all radars do occasionally, we have to do what's called a corrective maintenance visit. So what the techs try to do first, before they go out, they try to ascertain what the issue is with the radar, so that when they need to visit, they take the right parts with them. And sometimes the issues can be resolved via remote intervention. But if they got to go out to the site, that's another visit they have to do during the year. Whilst they're on site, they also do some maintenance, and first of all, they fix the radar. So that's the corrective maintenance within the Bureau network. So as I said, we're a bit earlier, we're always improving our radar network. So we have a number of radar sites coming up over the next few years. In Victoria, as I said, we just recently commissioned the Rainbow radar out in the Wimmera. Mildura is also, by the end of the year, will be upgraded to the dual pole digital Doppler radar at a new site away from the airport. New South Wales has 3 new sites in west of the ranges. So we've got a radar up towards Bourke, up towards the Queensland border at Brewarrina. That's going to be a new site. Heading a little bit further south inland is a new site at Hillston, and the most southern of the 3 radars will be at Yeovil, which is a town near Parkes. So there'll be 3 radars west of the ranges in New South Wales. Queensland as well is also getting 5 new radars. The first 2 are going to go up in the Burdekin and the Flinders River catchment areas, so around the townships of Richmond and Hewarden, around that area, so in between Mount Isa and sort of Townsville area. Heading down south inland from Bundaberg sort of area, we're going to put one in at Taroom. Also a radar in the Darling Downs area around Toowoomba, and also a radar that will fill in some gaps between the new radar at Brewarrina and the Namoi radar will be going in around the Goondiwindi town as well. We also got a couple being installed in the Northern Territory. So Tyndall, up near the RAF base at Katherine, is getting a new dual polarised radar, and we will be installing a new radar at Tennant Creek as well. Western Australia, we've just recently upgraded 3 radars, Albany, Esperance and Geraldton, in the last year or so. However, we were forced to do a replacement a little earlier due to the cyclone that went through the Pilbara back in February, where a Dampier radar got damaged beyond repair. So we will be replacing Dampier radar and putting it on a new site in the next year or so. And that's the future radar improvements.
Excellent. Fantastic. A lot of information there. I hope everyone is able to take something from that for you or your business. Now, we do have this great opportunity, like we keep mentioning, to ask our experts some questions. Now, we are going over time. We do appreciate your patience. We did have more questions than we factored for, so we're going to get straight into them now and answer as many as we can. About 10 minutes over. We're probably going to cap it at that. So Bronwyn wants to know, what effects does being 165 kilometers away from the nearest radar have on their ability to know what's happening on their farm?
I can take that if you like, Jordan. Look, 165 kilometres is in our optimum range of our radar. So back to our first poll question there, with the answer being between 5 and 200 kilometres per hour. You're actually in quite a good location. I mean, ideally, everyone would be in this sweet spot, but we're a very big country. But look, what it does allow us to improve our forecasting and our warning services to add this additional tool, the radar. So yeah, you're in a good spot.
Oh, excellent. Good.
Another interesting fact to that one, Kirsty, we actually cover 97% of the population.
Wow. So Thomas wants to know, what's the optimum height for a radar, or does this differ for the radius the radar needs to cover?
I can take that one, Jordan. Generally speaking, we like to get the radar up as high as possible within reason. If you go too high, the tower becomes too big and it sways around. So we generally try to keep it around 20 meters. And what that does, that gets our signal away from the ground. So we get what's called less clutter, so the beam doesn't hit the ground close to the radar as it's raising in elevation. So that's why we like to keep it off the ground, and it also keeps the beams clear of any obstacles that are around the particular area. So generally speaking, now most of our new towers are going in at 22.5 meters.
Okay. Simon wants to know, is there a stage during intense weather events where radars just receive too much information, like a cyclone?
Too much information. I think they can pretty much handle whatever they dish out. They can handle getting it back. I guess the issue, if you're finding too many targets or intense targets, that it is going to cause issues for further down that range from that beam. So you're going to struggle to get much information from further targets if you're hitting a very intense cyclone or thunderstorm.
Okay. Neville's asked a question, and just a quick yes or no, because we are running out of time. Can we expect all radars to be updated to Dopplers as years go by? I think that's one for you, Andrew.
I think we most certainly could expect that.
Excellent. Okay, so we also got an interesting question here from Stephen. Is the location that must use composite images like Port Macquarie subject to lower accuracy? I think that might be one for you as well, Andrew.
Port Macquarie would be sort of in between three radars, so the Grafton, Namoi, and Newcastle radars. No, it's still in the sweet spot from the Grafton radar. If you're using the composite image, just bear in mind that it's looking at all the radars in that coverage area. So I generally don't use the 512 myself. I usually go down to the lower scales and see what the best reflectivity is, and probably compare that to the satellite images just to back up what your thoughts are.
Okay, and last question, Thomas. Why is the radius 64, 128, 256, and then 512 km intervals?
Oh, that's an old kickback from digital, bit like your memory in a computer, 512K, 1024. You know, that's all that is. It's just a throwback from historical, that how we have our radars scaled down to 64, 128, and so on.
Okay. Actually, because you answered that so quickly, do have one more, Helen. If the radars are not ideal for use all the time, what other tools from the Bureau could be used, like satellite images, for instance?
I'd probably say satellite images. Look, both radars and satellite images are quite good spatially, so that's why they're heavily used. But obviously, anything that's like accurate information, like surface observations, are also great tools as well.
Okay, well, thank you so much, guys. That was an excellent and informative session, and I hope everybody out there enjoyed it just as much as I did. I learned a lot in this as well. We've got another another webinar coming up on the 19th of May. It's going to be on the impact of recent rain on water resources in the Murray-Darling Basin. There has been a whole bunch of information that's come out about that. But Kirsty, if somebody has come a little bit late, how can you summarize what you've spoken about today?
Well, we hopefully all learned that we've got the 4th largest radar network in the world. And hopefully everyone's taken away something about how radars work, the types of radars we have at the Bureau, and how we use them. Radars are a really fantastic short-term forecasting tool that we can use to improve our forecasts and warning services. And to get more information on our radars, you can check out some of the links on our webpage.
Yeah, or download the BOM app. There's always a radar that you could check out through there. That brings us to the end of today's webinar. As I did mention before, the Murray-Darling Basin Water Resources webinar, the link is going to be going into chat now if you'd like to join us. But for any of the questions that we didn't get to, you can email weatherquestions, that's one word, at bom.gov.au. A big thank you to Andrew and Kirsty for your time in developing the content and sharing your knowledge with us. And of course to you, thank you for tuning in and joining us today. We hope you enjoyed the session, and we hope you'll join us again next time. If you want to continue the conversation, please use the hashtag #BombWebinars in your social posts. As mentioned earlier, this session has been recorded and we will be emailing it out to you so you could watch it or share it with your friends in the next couple of days. So watch this space. And finally, but most importantly, we want your feedback. It's our aim to give you the highest possible quality webinar, but we can't do that unless you share your experiences with us. So this is going to close. A little survey will pop up, and we really appreciate you completing that anonymously for us. Once again, thank you for your time, and we look forward to seeing you again soon. Goodbye.